Last talk of the day. So let me start by thanking the organizers for inviting me to give this talk. That is about our recent work from a couple of months ago on homological quantum rotor codes. And this is joint work with Christophe Guillot, that is the first author of the paper, and Barbara Terral. And so as the title says, the talk will be about encoding quantum information starting from native systems that are rotors. So the first question we need to ask is, what's a rotor? So here, I would say that here we have a representation of what I think everybody would call a rotor, meaning a mechanical rotor or a pendulum, if you want, which is basically a system that is described by phase, defined in 0 to pi, and its angular momentum. But we also know that in circuit-QED, for instance, we have systems that behave like rotors, for instance, Cooper box, where now the role of the phase is played by the superconducting phase. So here on the left, I put some definitions of groups that will be useful during the talk. So from a quantum mechanical point of view, a rotor is a quantum system that can be described by a state that lives in a Hilbert space whose elements can be written as a linear combination of countably infinite states, like for instance, the angular momentum states, and so these states are obviously normalized. Or equivalently, we can take the so-called discrete time Fourier transform and also represent the system via a continuous wave function that is normalized in 0 to pi and is periodic. So starting from this system, we can define what we call generalized Pauli operators that are essentially translation operators in momentum and in phase. So I call the translation in angular momentum generalized Pauli X operators. So they are characterized by an integer m, while the translation in phase, they will be called generalized Pauli Z operators. And so they are characterized by a phase that is defined in 0 to pi. So obviously then we can take the same for n rotors just by taking the tensor product. And so now translations for n rotors will now be characterized by vectors that are either integer vectors or vectors with elements in 0 to pi. We can look at the commutation relations between these general Pauli operators, and it's easy to see that basically they commute if the inner product between their representative vectors, so m and phi in this case, is equal to 0 modulo 2 pi. All right, so we can already define this notion of homological quantum rotor codes, and we do it in a sort of CSS fashion. So basically, we start from two integer matrices, hx and hz. So one comment is that during the talk, I will always use vectors that are row vectors. So this is a bit counterintuitive, but it was the right way to write it. So basically, these matrices hx and hz are rx times n and rz times n respectively, and they satisfy this condition. So hx times hz transpose is equal to 0. So we can define a stabilizer group starting from these matrices, because this condition here simply implies that all generalized Pauli Z of this form and generalized Pauli X of this form commute. And so we define a stabilizer group starting from these native generalized Pauli operators. But now notice that this vector phi has continuous elements in so 0 to pi to the RZ, while this other one S has integer elements. So basically the homological rotor code is simply the subspace of the n-rotor Hilbert space that is stabilized by this stabilizer group. So let me comment on this definition. So first of all, so we see that the X and Z type stabilizers can be specified by Rx and Rz dimensional vectors respectively via this mapping here, basically. So they will be mapped to vectors that identify generalized Pauli operators by the Hx and Hz matrix respectively. We can use the same matrices to construct a qudit stabilizer code, simply because if this is true over the integers, it will be true also if we take modular in modular arithmetic. Since our native systems are rotors, so this maybe will be clearer later, we don't need modular measurements. And importantly, as we will see, we can encode rotors and qubits. So let me also introduce what we mean by syndrome. So this is kind of standard, I would say. So we start from a state in the code subspace, and we apply some Pauli errors. And then we see simply that these new states are, again, states of either the SZ or X stabilizers with now a different eigenvalue. And so starting from this eigenvalue, we can define the syndrome that, so basically the X syndrome will be given by this, so it will be related to the HZ matrix, while the Z syndrome will be related to the HX. So now we are ready to see the homological interpretation of this code. So basically, we, as we said, so we just stated for the X part. Essentially, we saw that we can represent stabilizers via vectors in Rx dimensional vectors of integers. So now these vectors, although technically speaking, I should call them modules, are mapped to identifier of operators that are n-dimensional vectors of integers via the Hx matrix. And in turn, these, we have just seen that they are mapped to syndrome via the Hz matrix transpose. And we know that by definition, Hx times Hzt is equal to 0. And so basically, this is the definition of a chain complex over Z. And so basically now we can use let's say, the standard interpretation of homological codes and state that the logical X operators are simply given by the first homology group of the chain complex over Z, which means that this is the intuition that the logical X are those operators that have trivial syndrome, but they cannot be generated by the stabilizer. So the construction is analogous for the Z part, but now we take the co-chain complex. Maybe just a remark here is that now notice that the co-chain complex is not anymore over Z, but is over T. So this is, let's say, a non-trivial thing of rotor codes. And so now the question, so what do we encode? So this can actually be completely understood looking at the Z part. Sorry, at the X part. And basically, it's known that this first homology group over Z of a chain complex can always be split into two parts. So that we call a free part, F, that is isomorphic to Z to the K prime, with K prime an integer, usually called the Betty number. And this just tells us how many rotors we are encoding. But then we see that there is another part that is called the torsion part, that is instead isomorphic to direct sums of cyclic loop of a certain dimension. And so basically, if we have a torsion part, we will also be capable of encoding qubits, for instance, of qubits. Importantly, the torsion comes from the fact that Z is not a field, so that we are starting from rotors, but only a ring. So basically, there is no multiplicative inverse inside Z. And so this is also the reason why when we consider qudits codes, we always encode other qudits. So we never have a torsion part because we take the a prime, for instance, it will be a field and not only a ring. So we can accordingly also organize the generator of the X part of the the logical X as a matrix where the first part will be associated with the free part and the second part to the torsion part. And so here I just give a general form of a generalized Pauli operator, where this part here is simply means that we can simply multiply by a stabilizer. And so a logical X will be characterized by this vector that has elements here. So in this G logical X. All right. So now we define an error model. To start, I would say we take an error model that is of random shifts in phase or momentum with a certain, so similar, let's say, to the GKT code. So with a certain probability distribution that we assume to be of this form, where we have two weight functions, Vx of m and Vz of phi, which we require, and we require them to satisfy these conditions that are quite intuitive. And in particular, we chose this form here for the two of them. And so for n rotors, we just assume n independent random shifts, where now we have a global wave function that is given by the sum. So global wave functions that are simply given by the sum of the individual ones. All right. So now we can use this error model because, let's say, as we have seen also today, there has been some discussion. Like the definition of a distance is always tied to a certain error model. And so here, this is just a recap of the previous definitions. So we define the X distance as basically the minimum weight, where by weight we mean this function here, over all the possible logical X operators. And analogously, we try to define a Z distance, but it's a bit less trivial to define simply because the Z part of the stabilizers is continuous. And so to cure this, we are actually defined by this Vz of phi that is simply capturing what is the weight of an error, of a certain error, when it would occur on the simple unencoded rotors. We can discuss this offline, this definition. All right. Then we can also construct the Hamiltonian of the code simply by making taking an Hermitian version of the stabilizers. So as you can imagine, the X part is a bunch of cosines of linear combinations of the phase variables, where the coefficients are given by the elements of the HX matrix. While for the Z part of the stabilizers, since they have a continuous nature, we can actually directly take a sum of, let's say, a linear combination of angular momentum operators, where again the coefficients are related to the HZ matrix. And so now we make a Hamiltonian out of it, and it's quite natural to take actually the square of this, so that this will look like kinetic energy term. And so in general, the Hamiltonian of these codes will have this form. I mean, obviously there is not a unique way of constructing this kind of Hamiltonians, but this is, we think, the way that is more physical. All right, let's look at an example. So as some of you know, we can construct qubit or qudit homological codes, starting from tessellations of surfaces. And the same is valid here. So for instance, here I take a tessellation of the projective plane, where basically the projective plane, we just have to identify opposite edges in this case. So this edge here is the same as here, and this edge here is the same as here. And so we put rotors on the edges. The faces will be X-like stabilizers, and the vertices would be Z-type stabilizers. Notice that it's important to take also an orientation of the faces. We can just take a face and see what edges are connected to it, basically obtain the HX part of the stabilizers, and the same for the Z part, where notice obviously this is redundant to this second row. So this encodes a qubit because the real projective plane has a torsion part, and these are possible logical X and logical Z. And we can also construct the associative Hamiltonian, so it will have this kind of kinetic term plus 2 weight 2 cosines and 1 weight 4 cosine. All right. So now we want to look at possible physical realization in circuit-QED. And spoiler alert, actually there have already been some circuits that are actually physical realization of these codes, but this wasn't realized before, simply because these codes didn't exist before our paper. So we want to realize physically a Hamiltonian that has a rotor code subspace as ground space. So this is the goal. And we want to do it in circuit-QED, let's say, using capacitances, inductances at Josephson junction. And so a big point is that since there is a code interpretation behind, so the code interpretation gives a way to understand directly which kind of errors the system should be capable of protect against. And I would add also, it will give insights on how to do gates. And in general, regarding the protection, you can expect that, at least for circuit-QED systems, large X distance should mean protection against flux noise, while large Z distance should mean protection against charge noise. So let us start actually with a negative result. So a no-go result for exactly encoding qubits. So let us suppose that we have a generic structure of capacitances coupled to connected to Josephson junctions. You can imagine that the Hamiltonian that comes from this circuit will not be a sum of commuting terms, obviously. So we have to resort to subsystem definition of subsystem codes that here I don't get. But anyway, so the claim is that if we consider subsystem rotor codes starting from this primitive, and in particular, all we need is that the Josephson junctions, so the cosine terms are weight 2. The system either encodes nothing in the rotor code sense, or it encodes logical rotors. So the claim is that in this system, we cannot encode logical qubits, so we cannot have torsion part. So to encode logical qubits, we need to resort to perturbative methods. So in the paper, we discuss details like this circuit that we call this 4-phase gadget. So this was also studied before in this paper by Weiss et al. And for the purpose of this talk, we'll direct, so in the paper, we also analyze some other regimes. But for the purpose of this talk, I just consider the regime we will be interested in. That is simply the case in which the capacitance, so this vertical capacitances here, are much larger than the other ones, so CG and CJ. And this condition in low energy will impose the constraint that, so now I still call L the number of Cooper pairs, that the number of Cooper pairs here plus the number of Cooper pairs here has to be 0, so 1 minus the other. And the same is valid here. And in addition, we consider the regime in which EJ is much smaller than the typical charging energy associated with the ground capacitance and the Josephson junction capacitance. And so why do we consider this regime? Because this circuit perturbatively will be, so in low energy and in this regime, actually gives rise to cosine, a 4-body cosine term, and let's say a cartoon of what is actually happening in terms of Cooper tunneling is depicted here. But let's go to the next slide, where we will use the fact that this square here will give a cosine. Yeah. And basically, in 2006, Kitaev proposed this current mirror qubit, which I think if somebody reads the paper is quite a mysterious paper. But anyway, so our claim is that this qubit that was also later analyzed again in this Weiss et al. Paper actually provides a physical realization of one of a particular homological rotor code, and it is associated to a tessellation of a Möbius strip. So a Möbius strip basically, so here we have a tessellation, and at the end there is a we flip the phase stabilizer. So you can again repeat the previous procedure. You will see that you now have for the X part, you see that so each edge here is a rotor. So you will have 1, 2, 3, 4 phases involved with a twist at the end, while the Z part is simply two body, and as you see is simply a sum of this Lj plus Ln plus J, which is reminiscent of the fact that a big capacitance will enforce this constraint. And indeed, now the circuit actually really looks like a Möbius strip. And the circuit is, so Kitaev's current mirror qubit or Möbius qubit is the following. And it's simply a repetition of these 4-phase gadgets in series. So, and sorry, with a flip. All right, so this encodes a qubit, simply because, again, Möbius, so the Möbius strip has non-trivial torsion, as you might imagine by thinking of how the Möbius works. So these are possible logical operators. And so the thing is that the X distance is fixed and equal to 2, and it does not increase let's say the more 4-phase gadgets you put, while the Z distance is increasing linearly with N. So you actually expect, so this system is protecting supposedly against only one type of error when you increase the distance, but not the other. So here I'll be quite short. So actually also the 0-pi qubit can be viewed in this way, but now as a rather trivial tessellation of the of the real projective plane. So to see it is a bit more involved, so maybe I will not go too much into details. So I conclude with an outlook of future directions, and I thank you for your attention.
Questions? Yes, really cool. There was a nice slide by Kyle where he had a whole bunch of other qubits.
Yeah, oh, yeah, indeed. Yeah, I forgot to mention. Yes.
So have you managed to make contact with any of these other designs?
Not existing ones. Actually, we have an idea to make. So, I mean, what we were looking during the project at was to try to, increase the distance in both directions. So Z and X distance. So we have an idea that for a circuit that could potentially increase the X direction, although it would have some other restrictions. But well, so far of existing ones, we didn't find let's say circuits that could be mapped to homological rotor.
Yeah, I mean, I just also find this useful for understanding current, like more experimentally relevant codes, where people cook up things using different designs that aren't necessarily rooted in hardcore CS error correction. But now I can understand.
Okay. Yeah.
So
yeah,
cool.
Indeed. I think this is a very cool thing that if you have the all the theory of error correction behind you, you kind of know where. I mean, it can also guide you in the design. Also, yeah, it's a cool thing. So I encourage people to build a current mirror qubit.
Great talk. So I have a really basic question.
Yes.
So a couple of years ago, maybe it's still ongoing, people were debating whether this phase variable was compact or non-compact.
Okay. Yeah.
In which case, if it's non-compact, then these superconducting settings aren't actual rotors, right?
Mm-hmm.
What's the current state of that debate?
I have, so my take is that, okay, so if you take a Cooper pair box, people might disagree. Huh? So if you take a Cooper pair box, so the important thing is that as long, so you can have like, let's say, you can treat it non-compactly, but then the rotor subspaces will not mix each other. So what I claim is that, you could as well describe, when you have charge noise with random charges. I mean, you could already say, well, actually, I'm already out of the formalism of quantum mechanics because I'm putting myself randomness in a quantum mechanical system. But then there is an equivalent description of that in which, you see the, let's say, the dephasing caused by charge noise as basically having, a mixture of different rotor subspaces with different eigenvalues. So I think they can I would say that they coexist in a certain interpretation, the compact and non-compact. If people disagree with this view, then.
Other questions?
Question from an experimentalist, so be warned. But is there a generalization of this homological construction to harmonic oscillators rather than rotors?
Okay, so what you could do is you take one of these codes, now at this point you can take harmonic oscillators, system of harmonic oscillators, and in each of them you impose that the constraint of the rotor subspace, which is basically that to the I 2 pi momentum has to be equal to 1. And so if you take oscillators and you take these codes and you impose this additional constraint, then you would have, sort of a GKP code that would have the same properties as this, but now you need modular measure in that case. Yeah, so yeah, the thing is, as before, like, the measurement frequency of, you only, in this case, you would only, in active error correction, you need to measure sums of angular momentum operators, which right now I wouldn't know how to do, but maybe some smart experimentalist knows how to do it.
There's another way to do it using these number phase.
Oh,
right?
okay. Yeah.
You have a fake rotor. Right?
Yeah.
So that, we're taking a look at that actually.
Okay, good.
Yeah, so I was curious about this fourth phase gadget. I think you
Yeah.
called it, which looks like a pretty simple circuit, and you're sort of saying it's already, non-trivial code. Like, would it be good for something? Should we make turn it into a qubit, or?
You mean only this?
Yeah.
Well, okay, it's not really it's not a code alone, I would say, but so actually, so this I discussed it in this perturbative version, but then if you now don't take this perturbative limit, I mean, you could, and actually, technically speaking, you should set really Cj equal to 0. I mean, then it would realize a rotor Bacon-Shor code, which, however, I don't know, it doesn't have like, it doesn't have like big properties. So yeah, but I mean, if somebody wants to play with it, yeah, be a start.
Okay, thanks.
Yeah.
All right. Any last question? If not, let's thank our speaker one more time.
Yeah.